All right, so I guess an exciting day today. We're starting our last big chunk of material, chapter 11, sequences and series, and we're starting in on sequences. There is a supplement for 11.1 that is up on YouTube, so that's in the supplemental videos playlist. So check that out after today's lecture. Um, I'm hoping that everything will dovetail nicely and we'll get through everything that we need to get through today. The quote of the day today is from my friend Mark from St. Louis. He's in finance, and he said this one time, and I wrote it down because I thought it was just a very succinct way to put it. He said, 10 times out of 10, I take a questionable contract with a solid person over an ironclad contract with a questionable person. And I think of this all the time when I'm dealing with like contractors, if you're trying to find people to fix your house or to work on your car or anything like that. Um, like having a written contract is nice, but if it's a shady person and you have an ironclad contract with them, like if something goes wrong and you have to take them to court, you've already lost, right? It's already turned out badly. Versus the person who, you'd be willing to take a handshake from, and if the contract is, not the most formal or not the most nicely written up contract, but this is a solid person, then they're usually the one I'm going to go with. Now, it is nice to have a contract just so that expectations are all laid out and everybody knows what each of their responsibilities are. So don't get me wrong there, but it's more about, at the end of the day, you're doing the deal with the person, not with the legal document. And and I hope that I usually try to be the kind of person who somebody would be willing to take a handshake from and not really rely on the contract. So that is the thought for today. It kind of dovetails in with the Marcus Aurelius quote, be one, right? Stop arguing about what it means to be a good man, be one. Okay, so moving on then to 11.1 sequences. I have been having a little trouble with my my Microsoft Office suite today. So I'm hoping that nothing goes wonky in OneNote, but I might have to restart OneNote or something. It it's been giving me this strange pop-up all day, and I tried to sort it out in between classes by logging out and logging back in, and then that created more problems. So fingers crossed that we don't have Microsoft Office snafus this afternoon. All right. So sequences. What is a sequence? Uh, let's just introduce the idea and talk about some examples. So a sequence, oh, why did it do that? It just jumped down. Okay. Sequence, it really is just a function, but it's a special kind of function that gives it some interesting behaviors. So it's a function, but whose domain is the natural numbers. So the inputs into this function are only integers like 1, 2, 3, etc. There's a little bit of flexibility here. I'll say just or something similar. Essentially, either the natural numbers themselves or something that can be easily made to look like the natural numbers. So maybe 2, 4, 6, 8, 10, or maybe you start at 0 instead of starting at 1. But things that have this kind of property where you have a starting number and then a next number and then a next number after that. So there's the concept of a next allowable input. If we think of a function defined on, say, the real numbers, or even say an interval, say closed 0 to 1, so f takes 0, 1 to r, something like that, the like first number that I can plug in, the smallest number is 0, but then what's the next allowable input? The next largest allowable input? Well, between 0 and any number bigger than 0, there's another number. If I say that maybe there's a number epsilon that's the next allowable input or some really small number, well, epsilon over 2 is a real number that's still positive, I have another one in there, right? So there's no real concept of like the next allowable input in our kind of standard functions with our standard types of domains. And that's what makes these sequences behave differently. So a sequence is a function whose domain is the natural numbers or something similar in the sense that there's kind of a starting number, and then for each number that is that's in the domain, there is a next allowable input, a next largest, or I suppose next smallest allowable input. So that's really what a sequence is. It's a function in the sense that each input generates a most one output. So I'll never input one and get an output of maybe 2 or maybe 7. So each input generates at most one output. But the main restriction here is that there's a starting number and then the concept of something like a next allowable number. So some examples, we might have the sequence, say 1/2, 1/4, 1/8, 1/16, etc. Or we might have the sequence 1, 4, 9, 16, 25, etc. Right? Or we might have a sequence like this: 1 and then 1 0, 1 0 0, 1 0 0 0, 1. We can see the pattern. Maybe even a sequence like this, the famous Fibonacci sequence, where uh, after the first two entries, then each next entry is the sum of the previous two. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. And we could think of lots of examples like this. Something that I notice is that with a sequence, I can actually enumerate every possible output, starting at the beginning and going up to a certain point. I can't really do that with a function over the real numbers. I can pick, you know, some output or some inputs and outputs, but I can't, there's always going to be more inputs and outputs that are kind of in between, so to speak, the ones that I pick. I'm picking a sampling, not all of them. But for a sequence, I can say this is exactly the outputs corresponding to the first 4 inputs. There's nothing else between these 4, so to speak. Now, quite often, I mean, it's nice enough to write out a sequence like this, and we can kind of see the pattern, but quite often we want to refer to algebraic structures. If I ask you, what's the 100th term in this sequence? Well, I don't want to have to write out 99 of these things. I would like an algebraic representation. Okay, so often I'll refer to my sequence function as A. It takes as input the natural numbers. And now note that as output, it has real numbers. So the range, in a sense, of a sequence is going to look like real numbers. So the outputs can be, they can be integers, but they can be fractions, or they can be decimals, or it could be like, I can have one that's like pi, pi squared, pi cubed, and so on. It could be transcendental numbers. The outputs can essentially be whatever. It's just the inputs that are restricted. It's just the domain that is restricted. And the notation that I'll often use is like this: a sub n, n equals 1 to infinity. or if the indexing is presumed, if it's clear from the context, if it's clear that that the inputs are 1, 2, 3, 4, 5, I might just concatenate this to the sequence AN. So for instance, this sequence, I could write it out this way and recognize the pattern, but two issues with that. One is, as I said, if I want the 100th or 1,000th element in the sequence, that's kind of hard to figure out if I don't have an algebraic structure to just plug 100 or 1,000 into. And also, I mean, strictly speaking, there's nothing that says the next one should be 1 over 32. I mean, this feels like a pattern to us. It's a recognizable pattern, this 1 over 2 to a power, but um, that just feels right. Could you come up with some other crazy function that when you input 1, it gives a half, when you input 2, it gives a quarter, 3, 1/8, 4, 1/16, and 5, 785? Yeah, sure, you could find such a function. So if we want to be either very clear and unambiguous, or if we want an easy way to figure out what is the nth element in a sequence, I might write something like 1 over 2 to the n. This is the sequence 1 over 2 to the n equals 1 to infinity. When n is 1, that's my first element, 1/2. 1 over 2 to the first, 1/2. When n is 2, 1 over 2 squared, 1/4. N is 3, 1/8, 1/16. And now, because I've made very clear what the kind of underlying function is that's generating these elements, we do know that the fifth element is 1 over 32, and then 1 over 64, and so on. And if I wanted to, I could plug in n equals 100 or n equals 1,000 and immediately just get the 100th or 1,000th element of the sequence. Something like this one, 1, 4, 9, 16, 25. I notice that these are squares, 1 squared, 2 squared, 3 squared. I think this is n squared for n equals 1 to infinity. For this next sequence, a 1 and then 1 0, and then a 1 and then 2 zeros, then a 1 and then 3 zeros, I can very clearly see the pattern, but I don't really know an algebraic representation of the nth one of these. So this is one where I can recognize the pattern pretty easily, and probably even a 10-year-old kid or 8-year-old kid or something could write out the next 20 or 30 of these and figure out the pattern. But if I asked you what's the 10,000th element of this, is it a 0 or a 1, you'd really have to think about it, right? I don't think there's an easy algebraic function to generate this list of ones and zeros, even though we can recognize a pattern. So just because we see a pattern doesn't necessarily mean we can easily infer what the algebraic structure is that would give rise to such a pattern. This one, there actually is, very strangely, there is a formula that gives the nth Fibonacci number. It looks something like, I forget exactly what it is, but it's something like 1 plus root 5 over 2 to the n, or maybe it's like 1 over n, and then like 1 plus, or maybe 1 minus root 5 over 2 to the like negative 1 over, it's something very strange like this that you're thinking, if I looked at this, I would bet good money that this was not even an integer, let alone anything meaningful like the Fibonacci number. But there is actually something like this that you can just plug in n and then generate the Fibonacci numbers, but it's quite complicated. So for things like this, where I naturally have a dependence of one element on previous elements, I have maybe a different approach that I can take that's a little bit more natural for these types of problems. Okay. So I can write out my sequence. I can just write out several elements and see the pattern. I can kind of refer to it that way. That's a little bit like the tabular method of describing a function from the reals to the reals. Or I can write it out this way, kind of algebraically. And let's do this last one, of course. This is just pi to the n equals 1 to infinity, just to wrap up that one. And then there's another algebraic structure that I can use for things like the Fibonacci sequence. This other structure, if you've done programming in the past, you might have come across this idea already, this idea of recursion. So you have kind of a base case, you have a starting place, and then to kind of move forward, you refer back to the starting place. And to move forward from there, you refer back to your previous work. So let's look at recursive definitions. So here I know something about how the ANs relate to one another, or in particular about how AN relates to, say, AN minus 1 and AN minus 2, right? So for instance, A2 equals A1 plus, starting at 0, A3 equals A1 plus A2. A4 is A2 plus A3. A5 is A3 plus A4, and so on. So for instance, this would be A5. It's A4 plus A3. Now I don't have that A2 is A1 plus something. So I need to start somewhere. I need to start with A1 equals 1 and A2 equals 1. And then I can go over to this recursive definition where the next one depends on some of the previous ones. So how would I define this Fibonacci sequence? I would define it as the sequence n equals 1 to infinity, where an is given this way. A1 equals 1, A2 equals 1, and let's say an equals an minus 2 plus an minus 1. So the n minus 2th index and the n minus 1st index get added together. And this is for n in, well, this is starting with n equals 3. So 3, 4, 5, etc. So if I need to know A1, I just look up A1 equals 1. If I need to know A2, I look up A2 equals 1. And then each next one, A3, I can compute as A1 plus A2 and get A3. And then A4, I can compute as A2 plus A3 and get A4. The plus side of a recursive definition is that once I'm kind of in the meat of things, once I'm, a little ways into the definition, I know how once I'm a bit of the ways into the sequence, my definition tells me how kind of locally things relate to one another. That's pretty nice. The downside is if I ask you, what's the 10,000th Fibonacci number, you need to figure out 9,999 other Fibonacci numbers to figure out the 10,000th one. You can't just plug in n equals 10,000 because the 10,000th one, you need to know the one before it and the one before that. And for each of those, you need to know the ones before them. You need to fill in the whole sequence up to that point and then get that one, right? I didn't have to, up here where I had a formula n squared or 1 over 2 to the n, I could just plug in n equals 100 or 1,000 or 10,000 and just get that one element. I didn't have to fill in the whole sequence up to that point. Yeah, but with these recursive ones, that's a downside. Um, Another example of a recursive definition would be the factorials. So n factorial is defined to be, well, we have 1 factorial equals 1. And I wrote that kind of strange. Here, I combined two different ways of writing it. N factorial is defined to be 1 for n equals 1. And well, for integers n, I know that, say, like 5 factorial is 5 times 4 times 3 times 2 times 1. It's the product of that integer with all other integers less than it, positive integers less than it. But I notice that this is 5 times 4 factorial. So n factorial is n times n minus 1 factorial for n equals, for n in 2, 3, 4, etc. So 2 factorial is 2 times 1 factorial. 1 factorial is 1. That's our base case. So for these recursive definitions, we need to have kind of a base. We need to have a starting point, and then we have an iterative step. We need to have somewhere to start, and then we need to say how each one relates to, say, previous versions of it. If you've ever done recursions like computing factorial or Fibonacci numbers in programming and didn't understand them, I was with you for quite a while. I was like, why is my program blowing up, or, seeming to get into an infinite loop or crashing or something? And really what it has to do with is each time, you have a factorial of n program, it's going to call a factorial of n minus 1, and that's going to call a factorial of n minus 2, and so on. So on your stack, you're going to put multiple instances of this program. This program is running many, many times. And it is super crucial that you have this base case written properly so that when you get to the top and you run into that base case, then this is 1, and that plugs it into the previous program, the previous, all the way down the stack. So you're just pushing instances of the program onto the stack until you get to the base case. And then as soon as you hit the base case, you just pop them off the stack one at a time. So if you're in a programming class and have trouble with recursions, I did too, until I understood what it meant to push something onto the stack, pop something off the stack, and how all of that worked. So, but this is, these Fibonacci numbers or factorials are the canonical examples of recursive definitions, either like in programming or in math. And in programming, there's like the towers of Hanoi is another one that, solving it with one more disk is basically like you solve it with one fewer disk, and then you move the disk, and then you solve it again with one fewer disk. So you like solve the n minus 1 smaller disks, you move those, you move the biggest disk one thing over, and then you move the n minus 1 smaller disks again, and then you move the biggest disk again, and then you move the n minus 1 smaller disks a third time. So being able to move n disks is basically the same as being able to move n minus 1 disks. And if you haven't seen the Towers of Hanoi, it's just this little game that the little puzzle you try to figure out. So you can Google it. Okay, so is there anything else I wanted to say here? Okay, so one thing that we do note is that if we wanted some kind of, so we talked about algebraic and essentially tabular like representations of our sequences. If we wanted something like a graphical representation of our sequence, like this 1, 4, 9, 16, 25, this n squared, I would not come down here and write something like this as a graphical representation of my sequence, because this kind of implies that there are a whole bunch of points, there are infinitely many points that are giving rise to this nice smooth line. Really what I have is like 1, 1, 2 comma 4, 3 comma 9, 4 comma 16. Oh, no, we're a little wonky, but 4 comma 16 like that. Now I can imagine that in the background I have a quadratic function and I'm kind of plucking points off of that. So if I wanted to draw this in like, lightly in pencil as an aid to help keep me going straight and then erase it, I don't see a problem with that. We can use some knowledge about the underlying real-to-real function to help us understand some things about the sequence. But we need to make sure that we understand that they're not the same thing, right? This is like the sequence n squared, or this is like f of x equals x squared. Okay, so let's talk about convergence of a sequence. Let's talk about limits of sequences. So sequence a sub n, this has a limit L and R, a real number. Well, what does this even mean? I just said the sequence has a limit L. I didn't say, normally I would say something like, limit as x goes to 3 of f of x has a limit L. Well, note that with a sequence, if this is my point of interest, I can't get arbitrarily close to the input, say n equals 3. I can't plug in, 3.5 and then 3.1 and 3.01 and 3.001. I can't plug in any of those. The closest I could get is either maybe 4 or 2, but I can't get any closer than that. So actually in a sequence, the only limit that makes any sense, the only thing I can, in some loose manner of speaking, get closer and closer to is infinity, right? I can go this way as far as I want. Okay, so I can say just simply sequence an has limit L and R, and that has to mean the limit at infinity. And what does this mean? This means that the elements of the sequence a sub n can be made as close as we like to L by restricting n bigger than or equal to k for some k. And if the sequence converges to a real number limit, then we say the sequence converges. So if the limit at infinity is a real number, the sequence converges to that limit. Now you might say, well, this is frustrating because now we need to develop a whole nother perspective on calculus, right? Or a whole nother perspective on limits. But nicely enough, this theorem here helps a lot, because basically we see that the idea of a sequence, the idea of a sequence is I'm taking points that are essentially a subset of the real valued function, right? This algebraic function n squared or x squared. In the sequence, I'm just taking some points that would be on my real-to-real function, plucking those out and forgetting about the rest. If every point on my real-to-real function, if when I include all the points, I limit to a certain value, then certainly when I only include some of the points, I've got a limit to that value as well. I'm being a little bit hand-wavy here with some of the details, but that is what our theorem says, that if our real-to-real function, little f of x, in the real world, and back in chapter 2, how we're thinking of that, if that limit at infinity exists and is the number L, and if f of n equals a sub n for our sequence, then the sequence an converges to L. Now, very importantly, the inverse and the converse are not true. In other words, if this limit does not exist in the real-to-real world, that doesn't mean that the limit does not exist in the sequence world. Or if the limit exists in the sequence world, that doesn't imply that the limit exists in the real-to-real world. It's hard to say real-to-real world. Like it's a lot of R's all at once. And let's look at a picture for why that might be. Let's consider a sinusoid, just like a compressed sine function. So here f is taking r to r, and clearly this limit at infinity does not exist. But I could imagine setting this up in such a way that my sequence, when n equals 1, was right at this peak, was right at height 1. And when n equals 2, I'm also right at the next peak at height 1. And when n equals 3, I'm at the next peak at height 1. What is my sequence? That's just the sequence 1, 1, 1 forever. That's just 1 for n equals 1 to infinity. Of course, my sequence converges to the limit 1. So even if my function itself is doing all kinds of wacky things, it is possible that my sequence, it's only looking at a subset of those points. It's only plucking out a few of those points. Maybe the particular points it's plucking out are well behaved, and we're kind of ignoring all of the other wacky stuff the real-to-real function is doing. But on the other hand, if the real-to-real function converges, maybe I'll just come off to the side for this. If the real-to-real function converges like this, this goes to 0 as x goes to infinity, then whatever points I pluck off of here, essentially all of the points on f of x are kind of headed towards 0. So whatever ones I pluck off of here have got to be headed to 0 as well, whatever subset I pick. So long, of course, as my subset is, going all the way off to the right, well, that's not good. I live on a one-way road and somebody just went up the road driving the wrong way. Been a bit of a crazy day today between Microsoft blowing up for me and then now somebody driving the wrong way on the road. I hope they're okay. And it's a busy road too. So haven't seen them come back yet. Anyway, so if the real-to-real function converges to a limit and we're plucking points off of it, then that sequence of points has to also converge. But if the real-to-real function does not converge to a limit, then we really can't say anything about the sequence. We would have to look at the sequence through a different lens. Also, nicely enough, really kind of, leaning heavily on this theorem, we have a lot of nice convergence properties for sequences that seem pretty similar to the analogous convergence properties for real-to-real functions. If sequences a n and b n are convergent and c is a constant, then the limit of the sum is the sum of the limits. Constants can come outside of the limit, so the limit for sequences is also a linear operator. Break sums apart, constants can come out. Just like real-to-real functions, the limit of the product's the product of the limits. The limit of the ratio is the ratio of the limits, as always with reasonable constraints. The denominator limit can't be 0. And the limit of something to a power is the limit of that thing raised to the power. So we can ask a question like this maybe. For what values of R is the sequence R to the n convergent? So let's write out a couple terms of this. And for sequences like this, we often started at 0. So let's do that here, just to demonstrate that we can have a sequence that, say, starts at 0. That's not a problem because we know we still have this very clear idea of what's the next input. Right? So I'm looking at R to the 0, R to the 1, R squared, R cubed. Or for this R to the 0, maybe I'll rewrite that as just the number 1. So this is a geometric progression. Each time I go one more to the right, I multiply by a factor R. Right? So to go from here to here, I multiply by R. Here to here, I multiply by R, and so on. It's a geometric progression. The sequence is going to be closely related to the geometric series in section 11.2, which is a very important series to understand. Okay, so really my question is, R to the n goes to 0 if absolute R is less than 1. I see that that has to be true, right? Why is that? It's because x to the n goes to 0 if absolute x less than 1. Right? It's basically, in the real world, the real valued function, um, we have that. So if I'm multiplying a number by itself over and over, that goes to 0 if it's less than 1 in absolute value. So we see that right away. We also see that R to the n goes to infinity if R is bigger than 1. If I take a number bigger than 1, like say 2, and multiply it by itself over and over again, that clearly goes to infinity. And R to the n does not converge if R is less than -1. I might have something like -2 to the first, which is -2. -2 squared is +4, and then -8, +16. It just flip-flops back and forth, but gets further and further away from 0 each time it flip-flops. Okay, so it does not converge here or there to a real number. And now let's look at the edge cases, R equals 1 and R equals -1. Well, when R equals 1, what's my sequence? It's just 1, 1, 1 forever. And pretty clearly this sequence converges to 1. So I actually do get convergence when absolute R is less than 1. And I do get convergence when R equals 1. And then my other edge case is R equals -1. What do I get there? I get 1, comma, -1 to the 1 is -1, and then +1, -1, etc. I keep flipping back and forth between 1 and -1. I can never say stay within 1/2 of any proposed limit. So this does not converge. So for what values of R is this convergent? This converges for R in the interval between 0 and 1, or sorry, between -1 and 1, not including -1, but including +1. Now, does that mean that our sequence r to the n is completely useless if r equals 2 or something? Well, no. I mean, it can go off to infinity the same way that, f of x equals x squared might go off to infinity if we go far enough to the right, but it's, it can be a perfectly reasonable model. So just because the sequence doesn't converge doesn't mean that it's useless or that, it's not going to model anything well. Things like this are quite useful in applications related to like mortgage and finance and present value calculations, things like that. So, but it just doesn't converge as we head off to infinity. It diverges if we're outside of this interval of convergence. Okay, so let's look at some additional examples. Let's determine the convergence properties of these following sequences. So the first one I have here is an equals 3 plus 5n squared all over n plus n squared. And here the first thing I'm going to ask is I'm going to look at my theorem, and if I have the real-to-real function converging, uh, then the equivalent sequence should converge to the same number. So I'm going to investigate f of x equals 3 plus 5x squared over x plus x squared. What happens to this as x goes to infinity? And I know the trick here. I'm going to divide top and bottom by x squared. And x over x squared is 1 over x plus 1. And I see that as x heads to infinity, this 3 over x squared and this 1 over x go away. And this goes to 5 over 1 or just 5. My real-to-real function converges to 5 as x goes to infinity. My sequence is just plucking out some points from that function. My sequence must converge to the same number. An has to go to 5. What about this next one? An equals n over 1 plus root n. Does it converge or diverge? For this one, maybe I'll stay in the an world, and I'll rewrite this as 1 over n plus, well, root n over n is 1 over root n. Well, what happens is I plug in larger and larger values for n, larger and larger positive values for n. Large positive values for n takes 1 over n to 0 from above. And really the same thing with 1 over root n. These are being added together. So I have two numbers being added together that are both heading to 0 from above. This heads to something like 1 over 0, or this is going to head to infinity. So this does not converge. This diverges. What about something like this? Again, I'm going to see if I can do some simplification here. If I think of the e to the n's like, I don't want to use x, maybe like w or something equals e to the n, I basically have w plus 1 over w over w squared plus 1. What could I do to simplify this? Well, one thing that I can do just kind of heuristically or like a rule of thumb to help me understand which way I should head here, I could say, okay, as n gets big, what are the dominant terms? Well, this e to the negative n, this e to the negative n goes to 0 as n gets big, so it's not going to really play a role. This plus 1 stays the same size, so I end up with something that looks like e to the n over e to the 2n, or like e to the n over e to the n all squared, or something like 1 over e to the n. I think this is going to go to 0. So does this go to 0? That's kind of what I'm feeling. Let's take a look. So if I have e to the n plus e to the negative n over e to the 2n plus 1, maybe if I divide top and bottom by e to the n, that's 1 plus e to the negative 2n over e to the n plus e to the negative n. Just multiplying top and bottom by e to the negative n. I suppose I could have even gone farther and multiplied by e to the negative 2n, but as n goes to infinity, this goes to 0, this goes to 0, this goes to infinity, and the 1 just stays constant. This is indeed going to 0. So we do converge to 0. Okay, what about the sequence cosine? This one's actually a little bit complicated. If I look at my real-to-real function cosine of x, at a glance, it seems like it shouldn't converge. But we remember that it is kind of possible to like strategically pluck out certain values like the peaks for my sequence, or maybe I end up at all of the zeros. Or maybe I just pick some input and then I get what amounts to being like 2 pi away each time, right? Maybe this is like, cosine of 2 pi n plus, 3 or something. So I could just happen to pluck out uh, points on this real-to-real curve to use for my sequence that like all have the same height. Or maybe that by happenstance don't all have the same height, but actually kind of follow a progression where they limit to a certain limit. It turns out that basically because I'm increasing by integer numbers here, and because n is, or cosine is 2 pi periodic, its periodicity, it's not like its periodicity is like a nice natural number, but it's a transcendental number. It turns out that this diverges. But at least as far as I know, it's quite difficult to actually prove this carefully. But basically what we're doing is we're just, in essence, almost like choosing randomly different heights along this cosine. So we're just going to keep getting numbers that kind of fill in the gap all the way from -1 to +1, no matter how far out we go. But that's not easy to see. We would have to kind of make an educated guess here, maybe have the calculator, plot out the first 100 of these or something and kind of notice that it's just kind of seeming to be all over the place and make a guess. I think a careful proof of this would be beyond the scope of this course, at least as far as I know. If somebody knows of a really elegant proof that is fairly simple, let me know. But I don't know of a nice proof to this. On the other hand, if I look at cos of n over n, my real-to-real function, I have 1 over n times cos of n. So my amplitude kind of looks like 1 over n, and then my my cos of n so this is f of x equals cos of x over x. And it looks something like this. I see that as I'm not worried about what happens at 0. I'm worried about what happens as I go off to the right. And I see it looks like it kind of settles down. It looks like it gets squeezed to a limit of 0 because I know cosine is in negative 1 to 1. And then I just have this 1 over x, right? So um, if I take g of x is, say, negative 1 over x, h of x is positive 1 over x, just these two kind of envelope functions that this is bouncing around between. I notice that g goes to 0 and h goes to 0 as x goes to infinity. And I also notice that, let's say, for instance, uh, for x bigger than or equal to 1, g less than or equal to f less than or equal to h. So my squeeze theorem implies that f of x goes to 0 as x goes to infinity. And then my theorem that I've been making use of this whole time says that an must go to 0 as well. So it converges. And like I mentioned before, with, say, an equals cos of 2 pi n, here we have cos of 2 pi, cos of 4 pi, cos of 6 pi. Here we are actually just plucking out all of these peaks. Here an converges to 1, even though limit x goes to infinity. Cos of 2 pi x does not exist. And here, x is a real number. So in this case, restricting to a sequence, I ended up just plucking out kind of exactly the right members from this continuous function f, where I happen to just get an output of 1 every time. So my sequence is just 1, 1, 1, 1, 1. And my sequence converges even though the real-to-real function does not converge. So if the real valued function converges, then the sequence converges, the associated sequence. But if the real function doesn't converge, then we can't really say anything about the sequence. We have to investigate the sequence separately. So what about something like this? Well, an we can simplify to 1 over n plus cos of 2 pi n. And we see that the limit of the sum is going to be the sum of the limits. This is going to go to 0 plus, and cos of 2 pi n is always 1. So 0 plus 1 or 1. So this should converge to 1. All right, and then let's look at oh, here I have the squeeze theorem written out explicitly down here, but let's look at one last problem here, where an is root n plus 1 minus root n. Now don't be careless here and don't try to make this root n plus 1 minus root n and make these go away. That's not right. We can't distribute an exponent over a sum or difference the distributive property only takes us one line on PEMDAS. So exponents distribute over multiplication or division, roughly speaking, and multiplication and division distributes over addition subtraction, but not two steps. So we need to do something else here. What can we do? Well, one of our famous Calc 1 tricks, multiply by the conjugate, root n plus 1 plus root n. So we get a difference of squares, and that undoes the square roots. And then, of course, we need to multiply by the same thing on the bottom, so we don't change the value. Now this gives me n plus 1 from my firsts. My outsides and my insides cancel. I get plus root n plus 1, and then minus the same thing, they go away. And then I get minus root n squared, or just n, over my denominator. Or this is just 1 over root n plus 1 plus root n, which clearly goes to 0 as n goes to infinity. As n goes to infinity, root n plus 1 and root n both go to infinity. They're being added together. Very important. If they were being subtracted from one another, I'd have like 1 over something like infinity minus infinity, then I would have to do more work. But since these are added together, the denominator gets big, the whole thing goes to 0. This converges to 0. Okay, so along with the squeeze theorem, and I have an example here. I think this is a straightforward enough example to kind of do on your own. So we discussed the squeeze theorem briefly already, but consider this example. Try to prove it on your own. If the limit of the absolute values is 0, then the limit of the individual elements, not absolute valued, must also be 0. So try to prove this. And then that'll bring us up to the supplement, where we'll cover the monotone sequence convergence theorem, some additional examples, and that should, I think, wrap us up for section 11.1. There are 11 sections, 11 or 12 maybe, in chapter 11. So we're going to be in chapter 11 for quite a while, solidly the next month or so. So this is really laying the foundation for chapter 11. So I would strongly recommend going through this material carefully, reading through the book, maybe reading ahead actually for 11.2 for Monday, because 11.2 is we're going to look at series, which are very closely related to sequences, but also kind of quite different. So having a really good understanding of sequences will help you see the similarities and, importantly, the differences between the two. We're going to evaluate series on the basis of sequences. So understanding convergence of sequences and what sequences are will help keep all of the terminology straight in your mind when we get the series, and it will help you to see how we're using sequences to help evaluate some characteristics of series. All right, so let me stop the recording.